Hello everyone, I'm Tung from Xian-Yu Machine Learning Department. Today I'm going to present our work on learning object dynamics that can generalize across camera viewpoints, object appearance, and arrangements. This is a joint work with Zhou Xian, Mihir Prabhudesai, Shamit, and Katerina Fragkiadaki. From one image of a scene, humans can imagine how the scene would change as a result of object physical interactions. Such physics understanding, often termed as intuitive physics, is a core common sense knowledge of humans that get developed at an early age. It facilitates us to conduct spatial reasoning in the 3D space and helps us to make sensible plans and actions for a diverse range of manipulation tasks. We identify three key properties in humans' mental physics simulations that enables us to work in the real world. First, since we are constantly moving, it is critical that the simulation can work under any view. Change in viewpoint can cause the input image to look drastically different in the pixel space. Yet, our mental simulations are unaffected by the change. Learning physics simulation that can work under any camera viewpoint is a critical but untackled problem. Second, the simulation can cover general object dynamics in the 3D space. In the 3D world, objects move in 3D. To cover general object dynamics, it is needed that the simulation can simulate 3D motions as opposed to 2D. This is in contrast to previous work that tries to learn object dynamics only in a 2D space. Third, our mental simulation can strongly generalize to varying number of objects, unseen object appearance, and placement. This allows us to cope with different object configurations we might encounter in the real world. In this work, we propose a learning-based object dynamic model that possesses these three key properties of humans' mental physics simulation. Given an input RGB-D image along with its corresponding camera pose, our model used geometry-aware recurrent networks (GRNNs) to transform the input into a view-invariant 3D feature map. GRNNs use similar transformation operation as SLUM. While SLUM methods compose multiple depth maps into a unified 3D point cloud, GRNNs compose image features computed from different views into a unified 3D feature map. Given the 3D feature maps, our model learns to detect objects presented in the scene and obtains object-centric features by cropping the feature from the 3D feature map using the predicted 3D bounding boxes. These object-centric features will be the input to a graph network to predict 3D object motion. Using the accumulated motion, we can enroll the model by explicitly rotating and translating object features in the 3D feature map. This is possible because an object will have its feature in the 3D feature map at a similar 3D location as it is in the real world. Here we visualize the 3D feature space when objects are moving. Object features move in the 3D space and they persist over time. Our model can predict reasonable object dynamic under any view. It can also use any number of input views. Since our model works with object-centric features, it is able to generalize to unseen object arrangement. Our model can learn object dynamic not only about object stacking and folding. We show the model can learn more complex object dynamics such as object pushing. When trained with 2 objects, it can generalize to more objects. We outperformed by a large margin existing approaches which either use no visual input or use 2D visual features, which is not invariant to viewpoint change. Using the learned object dynamics, we can run NPC for the robot to push an object to a target location. Since the dynamic model is view invariant, the resulting manipulation model is also view invariant. It can work under any viewpoint. Besides, we show the model can directly transfer to a real robot platform. When we set up the robot, we do not need to fine-tune the pose of the camera to make it work. We can further use the model for obstacle avoidance tasks. The goal of the task is to push an object to a target location without colliding it with any obstacle in the scene. Since our object detection is in 3D, it becomes easy to detect whether 2 objects collide. Here we show the model can generalize to obstacle avoidance tasks on the real robot with unseen objects and object arrangements.